Let's see an example of the central limit theorem. So this problem is going to be a pretty long one. And initially, we're not going to use the central limit theorem. We are going to need the central limit theorem when we start asking questions about the average of a variable. So we're not going to use that until that second part. But let's begin. We have an elevator that states it has a maximum capacity of 4,000 pounds or 22 people. Let's study the equivalence between these two upper bounds. So 4,000 pounds or 22 people. Because men have an higher average weight than women do, at worst, all 22 people on the elevator are going to be men. So let's assume that we're dealing with men's weights. Men's weights are normally distributed with an average of 190.8 pounds and a standard deviation of 22 pounds. So on average, how much can each man weigh? Well, we have 4,000 pounds, and at worst, we're assuming 22 people on the elevator are men. So 4,000 divided by the 22 men gives us an average weight of 181.82 pounds. This is pounds per man. So on average, each of the 22 men can weigh 181.82 pounds and will be at that threshold of 4,000 pounds. Let's give the probability that a man weighs more than this. So we can do this because we know what the distribution of weights of men looks like. We know that they're normally distributed. So let's label our x-axis. In fact, I want to move that down a little bit so we can put some points on our x-axis too. This is men's weights measured in pounds. Okay, and where's the center of this distribution? The average weight of a man is 190.8. So it's going right here in the center, 190.8. And our standard deviation for the weights of men, 22 pounds. Okay, so what is the probability that a man weighs more than 181.82? 181.82 is somewhere over there to the left of 190.8, right? Somewhere on the left of your average. And the probability of weighing more than that is the area underneath the distribution on the right side. So I'm asked to find the area underneath a normal distribution. I need to turn this into a standard normal distribution by looking at z-scores. So what is the point of interest? What is the z-score of 181.82? So z-score is point minus average divided by standard deviation. We've done this a million times by now. So what is 181.82 minus the average? 190. What was the average? 190.8 divided by the standard deviation of 22. So we have a z-score of 0.4. Let's say, oops, should be negative. Let's say minus 0.41 after rounding. So this point right here is minus 0.41. So we need to use our z-score chart. So if you have a z-score chart that has negative z-scores on it, then you're done, or areas to the rights of negative z-scores. But I only have that one chart, so I need to translate this into areas to the left of positive z-scores. And I can do that pretty easily by symmetry. Right, the area on the right-hand side of minus 0.41 is the same as the area on the left-hand side of positive 0.41, right? These two pictures, because our normal distribution is symmetric, that's the same area. And this area right here, I can get from my z-score table. So let's navigate over to the z-score table and find the area to the left of 0.41. areas to the left of z-scores. So 0.41 is right here. So 65.91. So the probability is 65.91%. Okay, now notice we haven't used the central limit theorem here. We're just finding the areas underneath normal distributions. Now at this part, we will use the central limit theorem. Now we're asked a question about the average weight. So let's find the probability that 22 men in an elevator will have an average weight greater than the elevator allows. So let's remind ourselves of what the central limit theorem states. The central limit theorem tells us if we have a variable that's distributed with an average and a standard deviation, then this is going to imply that the average of that variable is normally distributed with the same average and now a smaller standard deviation, where n is the number of data points that are giving you an average. So notice the points here. I could start with any distribution and the averages will be normally distributed. Both distributions share the same average, so they share the same center. Your standard deviation changes though. So if we knew that the weight of men were normally distributed with an average of 190.81, so the weights of men were normally distributed with an average of 190.81 and a standard deviation of 22, and that is going to imply that the average weight of men is also normally distributed with the same average, but now your standard deviation is given to you by your original standard deviation divided by the square root of n, and we're taking the average weight of 22 men on the elevator. So when we go through this, we see that the average weight of men normally distributed with the same average as the original distribution, and now the standard deviation of the average weight of men is 4.69 after some rounding. Okay, so now that we know the average and the standard deviation, we can draw a picture. Right? It's still normally distributed. And this is the distribution for the average weight of men. In fact, it's the average weight of 22 men. Now, where's the center? It's still at 190.81. That's still the average. It's kind of strange to think about. It's the average of 22 men. And now our standard deviation is 4.69. But because we know what the distribution looks like, we can answer any questions that we're given. So what are we trying to find? I want to find the probability that 22 men will have an average weight greater than the elevator allows. So we found in the previous problem that the elevator would allow an average weight of 181.82. So what's the probability that 22 men have an average greater than 181.82? It's the area underneath the distribution on the right side of 181.82. So again, we solve this in the exact same way. We need to turn it into a standard normal distribution and look at z-scores. So this table will be the z-scores of the average weight of 22 men. All right, now because we have a different standard deviation, we're going to have a different z-score. So the z-score of 181.82 is 181.82 minus the average, 190.81, and then divided by the standard deviation of this distribution, that's 4.69. You get a z-value of about minus 1.92. So again, my table only has positive z-values, so I need to rewrite this as the area to the left of positive 1.92. Oops. Okay, so let's navigate to our z-score chart. 1.92 is right there. So 97.26% of my area is to the left of 1.92. So the probability that 22 men will have an average weight greater than the acceptable average of 181.82 is almost certain, 97.26%.